Hi, my name is Ben. I'm currently starting my PhD at the Center for Digital Music at Queen Mary University. And today I'll be presenting a study I conducted with my supervisor Saitis on the semantic dimensions of FM synthesis. And this work forms part of a larger project into facilitating more intuitive sound synthesis. Why might we want to do this? Well, for one thing, synthesizer controls generally not well related to the perceptual attributes of the sounds they create. Instead, they tend to map onto the parameters of the underlying synthesis mechanism, be it a DSP algorithm or analog circuitry. They also tend to be highly interdependent, which renders sound design somewhat inconsistent and unintuitive, typically requiring intimate knowledge of the working of a particular synthesizer to intentionally achieve a desired result. There's been plenty of work into synthesis control, and in particular linking it to perception. Recent applications of deep learning, such as the work of Philippe Esling's ACIDS group at IRCAM, using variational inference, have had some really interesting and encouraging results. If you're not already familiar with their work, I highly recommend checking it out. Very cool stuff. One issue we face, though, is that we're still relying on insights from perceptual studies on acoustic or physical instruments. And this is because timbre studies largely do focus on physical instruments, disproportionately from the Western tonal music canon. Synthesized sounds have been in common use in these studies since John Gray recommended their use as a method for creating sort of tightly constrained recreations of physical instruments. There's also been some work using synthesis to create controlled stimuli with the aim of eliciting particular psychophysical responses. But I would argue that there is merit for a number of reasons to studying synthesized timbres as sound objects and aesthetic ends in their own right. Firstly, they are valid musical entities, as the last century plus of electronic music history would demonstrate. Secondly, we can distinguish them by their timbres, so surely studying them is going to tell us something about the way we do perceive timbre. And thirdly, we should question whether previous timbral insights even still apply to the way a modern listener perceives sounds. Perhaps our ears have shifted to accommodate the changing palettes of modern electronic music. So the work of Zacharakis et al. In 2014 established the three-factor luminance texture mass model of timbre semantics, and similar looking dimensions have been observed in other studies. Luminance here, by the way, corresponding to English terms such as bright or sharp, texture to terms like rough, harsh, and mass to things like full, rich, thick, deep. And these dimensions were arrived at via exploratory factor analysis of semantic ratings, and they were derived from the sounds of familiar acoustic and electroacoustic instruments. So what we're hoping to understand here is whether they are applicable to the sorts of abstract and synthesized sounds produced by FM synthesis. So to study this, we designed an experiment. We gave our participants a synthesizer programmed to make a particular sound, and we instructed them to alter its parameters to create a new sound that matched a descriptive prompt, like make this sound brighter or make this sound less rough, etc. Once they were satisfied, we asked them to compare the starting sound and the final sound on a number of semantic scales. So that process constitutes one trial, and each participant undertook 9 trials. So that was 3 pitch conditions and 3 prompt conditions. And this inversion of the normal timbre semantic paradigm was inspired by the recent work of Zachary Walmark and co-authors, who prompted participants to find sounds matching a prompt in a 2-dimensional space mapped to the controls of an FM synthesizer. We recruited 30 participants for our experiment, all of whom spent their formative years in an English-speaking country. They all self-reported as having synthesis experience, and so they were largely music producers, sound designers, etc. And they all completed 2 subscales of the Goldsmith's Musical Sophistication Index, and we saw higher levels of musical training and perceptual abilities in comparison to the general population. Before going any further, by the way, I just want to take a moment to get everyone on the same page about FM synthesis. I'm sure most of you are familiar, but for those who aren't, it's a method for synthesizing sound by modulating the frequency, or strictly speaking, the phase of a periodic function with the output of another periodic function. It tends to generate very rich spectra, so most usually the functions used are straightforward sinusoids. Has a very broad timbral palette, and it generates quite complex patterns of harmonic and inharmonic partials. It's very popular for making metallic bell-like sounds and questionable 80s electric piano sounds, but these are just popular because they're quite straightforward to create. Its timbral range is much broader than this. So our participants used a 3-operator FM synthesizer. An operator in FM speak is simply a sinusoidal oscillator with a phase modulation input, usually paired with an amplitude envelope. You see more features in some synthesizers, but this is the core functionality. 2 of our operators modulated the phase of the remaining operator in linear combination, giving us 1 output node. And the gain and tuning parameters of this output node were fixed to control for pitch and amplitude effects on timbre perception. Each operator had an independent ADSR envelope. We use this shape because it matches what's found in most modern software FM synths. It's therefore more likely to be familiar to our participants. It does differ from the multi-stage linear envelopes you find in classic FM synths like Yamaha's DX series, but these sorts of envelopes have kind of fallen out of favor in everything except emulations of that original series. And we used a linear attack portion and exponential decay and release portions to match the envelope from Ableton Live's operator synth, which is a particularly popular modern implementation. So this is the web-based interface that participants were presented with, currently programmed to make what looks like a pretty horrible sound. You'll notice the tuning controls are separated into coarse and fine, and this is fairly standard in FM synthesis. Both of the controls combine to form a ratio of the fundamental frequency. And fine operates at just 1,000th of the resolution of the coarse control. Worth pointing out, by the way, that this experiment took place online because of the COVID-19 pandemic. So it's common to source descriptors for timbre semantic studies by analyzing corpora of orchestration or timbre literature. So in the same vein, we extracted our descriptors from a corpus, but to maximize appropriateness to the electronic sounds we're using, we formed our corpus by mining all the public posts from a popular modular synthesis forum, the regrettably named Muff Wiggler. These were filtered to bigrams that suggested a timbre was being described, and the resulting list was frequency sorted and pruned according to a set of criteria, and this left us a list of 27 descriptors, and here they are. So you'll notice we've highlighted 3 at the top, bright, thick, and rough. And these are the words with the highest frequency in our corpus that also loaded highly onto Zacharakis and co-authors' luminance, texture, mass factors. And these are the words we used as our 3 prompts. We selected them this way to ensure that we were eliciting variance along these 3 luminance, texture, mass dimensions. So one tricky subtlety of inverting the normal timbre semantic paradigm like this is that if we start everyone from the same set of synth patches, we risk biasing our data set towards the properties of only small subregions of the synthesizer's parameter space. For example, our participants often increase the gain of a modulator when they were prompted to increase the brightness. But this introduces more characteristics to the sound than just the brightness. And exactly what these characteristics are depends upon the position of many other controls, such as the tuning of that modulator. So if we depend on a small set of starting sounds, we only see a narrow slice of this range of characteristics, and it's difficult to determine post hoc whether these are properties of the starting set of sounds or of the synthesis method itself. So how to deal with this? We could start from random points in parameter space, but it's a very big place, and most of it doesn't really sound like the sort of sound a human would create using that synthesizer. So instead, we reuse the patches that previous participants created. So we're essentially growing outward across parameter space. So when you take part in the experiment, your starting points are randomly selected from the database of previous participants' synthesizer patches, and a set of 9 starting patches was created to manually kick off the process. And patches can never traverse pitch conditions, so nothing's ever heard at a pitch other than the one it was created at. So on to results. We performed a hierarchical cluster analysis on our descriptors, and we saw encouraging groupings of closely clustered descriptors. For example, noisy, gritty, harsh, etc. Percussive and plucky clustered closely together. Thick and big, dull, warm, mellow, smooth, clean, clear. The sorts of things you might expect to see. To identify latent semantic factors, we applied exploratory factor analysis. There's pretty extensive and heated discussion in the factor analysis literature about how best to select a number of factors. I'm not going to go into it now, but if you check out this paper by Fabregat et al., there's a pretty comprehensive review and comparison of methods. But what we settled on is Horn's parallel analysis method. And it's essentially a bootstrap approach in which the factor analysis is performed on a large number of normally distributed random data sets with the same shape as the real data. You then compute a threshold statistic from the eigenvalues or sums of squared loadings, normally the 95th percentile, and the number of values of your real data that exceed this statistic are taken as the number of factors. So here, parallel analysis supported 5 factors. This is the zoomed in relevant region of the plot. So here are our loadings. So what we're looking at right now are just the loadings with an absolute value greater than 0.7. And these are what we use to get a sense of the semantic underpinnings of each factor. We can also look at the full loadings of each factor. And what we see is that our first factor shows strong loadings for terms that have been associated in previous studies with luminance and texture. For example, sharp and bright, and harsh and metallic and noisy. And our second term for terms associated with mass, like thick and big and negatively thin. Our third through fifth factors, however, are a little less familiar. Factor 3 seems to associate with clean and clear, factor 4 with percussive and plucky, and factor 5 with raw. So we can look at their correlations to see how they relate, and when we do, we see these factors aren't entirely independent of the first 2 factors. So the clean, clear, clarity factor has slight negative correlations with both the first 2. Pluckiness factor has a slight positive correlation with sharpness, and rawness slightly less so. I should say, by the way, that these factors were subject to a non-orthogonal rotation after the factor analysis, which is why correlations between them are possible. And amongst these 3 new factors, we see like a moderate degree of collinearity between them, with the strongest relationship being inverse between clarity and rawness, unlike the first 2 factors, which are much more independent of each other. So what does this imply? It's possible that there are domain-specific specifications of existing luminance texture mass dimensions. For example, frequency modulation synthesis gives very fine control over the texture. So rawness and clarity could reflect subtle differences within texture, which represent enough variance in our data set to warrant entirely separate factors. There could also have been a priming effect of requesting these ratings directly after asking participants to synthesize these sounds. Maybe this encouraged a more sort of highly specified way of thinking than if they were hearing these sounds for the first time. We can also look at how factor scores varied in response to particular prompts. And that's exactly what these plots are showing. So here, blue represents a positive prompt, like make this sound brighter, and red represents a negative prompt, like make this sound less rough. So for each factor, we can see how the distribution of scores along that factor changes depending on which prompt was given. So we see big shifts along the first factor, the sort of joint luminance texture factor, with prompts for bright and rough, suggesting it quite likely is a combined luminance texture factor. And similarly, we see distinct big shifts along the mass factor with prompts for thick. The picture's less clear for clarity, ironically, associated to some degree with all prompts, but with pretty spread out distributions, but mostly with negative roughness. The fourth factor, the percussiveness pluckiness, is similar to the first factor, just with much wider, less specific distributions. And rawness associates a little with brightness, but again, mostly with roughness. So it seems that the clarity and rawness factors mostly vary with textual prompts, suggesting that they may be textural specificities. Luminance and texture being linked in the first dimension like this does also make sense in the context of FM synthesis. It's very difficult to say, increase the perceptual brightness of a sound without also introducing dissonant partials and increasing the roughness, altering the texture to some degree. So to summarize, we've seen a 5-factor semantic space for sounds produced with FM synthesis in response to semantic prompts. The first 2 dimensions of this space clearly relate to luminance and texture dimensions from previous studies. Sorry, luminance, texture, and mass dimensions, I should say, from previous studies. We've also seen some evidence for a percussiveness dimension, which is congruent to some degree with the suggestion made by Asterios and Kostas in their 2016 follow-up to the original LTM study, in which they also saw some evidence in favor of adding a percussiveness dimension to the model. We also saw some evidence for some more highly specified textual dimensions, rawness and clarity. It's probable that they are, at least to some degree, domain-specific to FM synthesis. Along with these results, we presented a novel paradigm for studying the semantic associations of synthesis methods, and the source code for this study is available in a GitHub repo. We're also sharing the data set of semantically tagged FM synthesizer patches, and this is also available on GitHub at these links. So from here, where next? The first step, which we have completed since submitting this paper, is an acoustic analysis of the sounds produced in the experiment. You can expect more details in due course, but for now, the results appear to support our interpretations. The next step, which we've also recently completed, is a follow-up study on a representative subset of the sounds. And this involved both a pairwise dissimilarity component and an absolute semantic rating component. Again, expect more results in due course. And from here, we can hope to begin to apply these insights and data to deep learning approaches to synthesis control. So we've had promising early results training metric semantic embedding models on the ratings we've collected. And we aim next to use this data to direct the control of generative models via latent space organization, conditioning, and other techniques. So that's all I have to share with you. We've got a couple of slides of references. I'll make sure to share these somehow after the presentation. Otherwise, thanks for your time and for having me, and I'm happy to take any questions.
So thanks very much, Ben. Time for questions. Any questions? No hands rising?
Hands rising. How do I do that?
Okay, I think that we have Professor McAdams with us.
Hello, can you hear me?
Hello, Professor.
Okay, hello.
Yeah.
Thanks, very interesting work, Ben. I have a question. I don't quite understand how you get from people's adjustments to their ratings and then to your factor analysis. Could you just walk us through a little bit through what the data were that you're actually collecting? It's a little bit unclear for me. Thanks.
Of course, thanks for your question. Yeah, I did rush through that a little. So the procedure was first of all this synthesis component where they were presented with a synthesizer configured to make a particular sound and a prompt, and they altered the parameters to create a new sound. And then subsequently to this, they compared the starting sound and the sound that they had created along a number of semantic scales, which, if you just let me find the slides, yes, were given by these descriptors here, which we extracted from the corpus analysis. And then the factor analysis, which we just presented, was on these post-hoc ratings. So we didn't present any analysis today of the actual synthesis decisions made in response to the prompts.
Okay, but you do have access to that. That's part of your acoustic analysis. Next stage is the actual values that they entered into, the sounds that actually created to make those semantic judgments.
Exactly, and all that data is present in the data set. I linked on that final slide as well.
Okay, great, thanks.
Thank you.
Professor Cariani?
I'm really sorry, I'm not getting any audio from you.
Yeah.
I just tried to, can you hear me?
Yeah, that's perfect.
So are people working on synthesizers where you have sliders that actually correspond to these perceptual dimensions so that, you know, you could get what you want in a more direct and simple and intuitive way?
I mean, that's one possible and hopeful outcome. I think, yeah, there's some obstacles to achieving that. Most pertinently, perhaps, the sort of many-to-one mapping between actual sounds and their semantic descriptions. But yeah, there's already been some really interesting work in this direction, and I'd refer again back to the work of Philippe Essling and his ASIS team at IRCAM. So their 2018 generative Timbre space paper and 2020 FlowSynth paper both take steps in this direction, one of which using a perceptual Timbre space to sort of organize the configuration of a latent space, and and another using sort of semantic tags and normalizing flows to enable you to move around a sort of semantic space with disentangled semantic dimensions. So yeah, I think there are already steps in this direction, and I hope more. I think it's a bit early to say whether these specific 5 dimensions will be the ones, but but yeah.
Good. Thank you.
Thank you.
Any more questions? If there's no more question, I would just like to add a point that you already been highlighted in your paper, that in the discussion, that it is a challenge to increase the energy in high frequency components by increasing the modulator tuning or gain without also increasing in harmonicity. And I would like to set it into discussion and for further thinking, because it's something that have also bothered us lately, the relationship, the interrelationship, and this interlace between manipulating parameters of various synthesis types without affecting other modalities such as the inharmonicity. So there's so much work to be done. Thank you very much.